Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss the precise definition of a limit. The precise definition of a limit is somewhat technical, which we'll be looking at. You should keep in mind that the intuitive concept of a limit is the most important aspect of what you should be learning, but the precise definition of a limit is also good to try to understand. Keep in mind that when you first run into the precise definition of a limit, it's probably going to be too complicated for you to understand completely, but keep trying because over time it will begin to make sense. In fact, calculus is really a couple of thousand years old, really going back to Archimedes. But in fact, it's only been a little over 100 years that mathematicians have been able to develop the precise definitions that we need to actually make the concepts of limit precisely clear. Limit of a function. Let f of x be defined on an open interval about x naught, except possibly at x naught itself. We say that the limit of f of x as x approaches x naught is the number L, and write limit x arrow x naught f of x equal L if for every number epsilon greater than 0, there exists a corresponding number delta greater than 0, such that for all x with 0 less than absolute x minus x naught less than delta implies absolute f of x minus L less than epsilon. Now, what makes this definition so confusing at first is it's not just a simple statement like you're used to dealing with in mathematics. It has what we call quantifiers, phrases like for every, and there exists, and such that, and so on and so forth. This begins to look like a legal document. Well, in order to get an idea of what's going on here, first, what you need to keep in mind is what this for every epsilon there exists a corresponding number delta means in particular is that this delta depends on that epsilon. It also depends on the L and the F, and the x naught. If I change the x naught and I change the F and the L, everything's going to change. So to begin with, we've got a fixed function. We'll fix the point x naught, and we'll fix the limiting L that we're going to try to show as the limit, or that we would test to see if it's the limit. And then in that case, the only thing that varies now is the epsilon. As epsilon would be made smaller, the delta will also have to be made smaller, and so you can think of the delta as being tagged by an epsilon, which might make it a little clearer. Now, in picture terms, if I look at the graph of a function, and so let's think of the x and y axes here, and here's some curve representing the graph of a function. Here's the point x naught. Now, at this point, let's imagine that either the value of the function there is L, or the value of the function may be there, or it may not even be defined. It doesn't matter. The point is that the intuitive concept of the limit is that without looking at what happens right here, in other words, if I draw a vertical line right through there, and I say, okay, you can't see whether or not the function has been defined there or what its value is. It's all been covered up. Can I tell what the value should be? Well, looking at the nearby points, that is x not equal to x naught, and of course that's a consequence of 0 being less than that absolute value. You can see clearly from the picture that it appears that this value is what the nearby parts of the curve are telling us the function should have at the point x naught. And so that would be our limiting value L. Okay, now there's a big difference between saying, well, I know a limit when I see it, I just don't know how to define it, and actually being able to define it precisely. And it's this complicated logical statement that actually makes that precise. What it means pictorially is that if I take a little roadway here that's horizontal, notice a little roadway, we can think of the line right through the limiting value y equal L as the center stripe of that horizontal roadway. Notice that I can find a vertical roadway narrow enough. It's got to be pretty narrow here, so that no matter what x I take down here on the x-axis, when I go up and hit the curve, the entire part of the curve over this little bit, the entire part of the curve that's inside the vertical roadway must in fact be entirely inside the horizontal roadway. You can see that if I make the horizontal roadway narrower, then this vertical roadway I've drawn may no longer work, but by making it still narrower, it will work. Well, let me draw a more magnified picture so that you can see it more clearly. So here is the graph of the function. Here's the limiting value y equals L. Here's our x-axis. And so maybe we've chosen an epsilon here. And don't worry about the fact that the picture is a little wobbly. It's the idea that's important. So here's our horizontal roadway, and there's the center stripe. Here's the curve F. Now, clearly, here's x naught, the vertical line x equal x naught. Clearly, I can make a vertical roadway whose center stripe is the line x equal x naught, so that when I look to see what part of the curve lies in the vertical roadway, that entire part of the curve also lies in the horizontal roadway. If somebody comes along and says, well, make the horizontal roadway narrower, notice my vertical roadway that I've chosen initially no longer works, but I can come along and make the vertical roadway still narrower so that my little narrower roadway now will work for the narrower horizontal roadway. And that's the idea of for every epsilon, there exists a delta. Delta here is the radius, in effect, of the little vertical roadway. That's the distance from the center stripe to the edge. The epsilon is the distance of the center stripe to the edge of the horizontal roadway. And so the idea that for every epsilon there is a delta, you can think of as that no matter how narrow we make the horizontal roadway, we can make the vertical roadway narrow enough so that the part of the curve that's inside the vertical roadway will be entirely inside the horizontal roadway. Well, sometimes you're going to be given problems where you actually have to find the delta given the epsilon. Let's look at a procedure for doing that. How to find algebraically a delta for a given f, L, x naught, and epsilon greater than 0. The process of finding a delta greater than 0 such that for all x, 0 less than absolute x minus x naught less than delta implies absolute f of x minus L less than epsilon can be accomplished in 2 steps. Step 1, solve the inequality absolute f of x minus L less than epsilon to find an open interval a comma b containing x naught on which the inequality holds for all x not equal to x naught. Step 2, find a value of delta greater than 0 that places the open interval x naught minus delta comma x naught plus delta centered at x naught inside the interval a comma b. The inequality absolute f of x minus L less than epsilon will hold for all x not equal to x naught in this delta interval. So we're going to be approaching our elementary problems here in this 2-step fashion. And one of the things I want to point out first, When I look at this inequality, absolute f of x minus L less than epsilon, that is equivalent to L minus epsilon less than f of x less than L plus epsilon, which is in a sense saying that f of x is in the horizontal roadway with center stripe L. Notice whenever you see absolute value, if you see something like, let's say, absolute value of A less than epsilon, that's the same as saying negative epsilon less than A less than epsilon. So this inequality is the same as saying f of x minus L itself is between negative epsilon and plus epsilon, so on adding L to both sides we get this simple inequality. So keep that in mind. When you go to attack step one to solve that inequality, this is generally the best way to go. Immediately replace it by this inequality, and now you have something that you can solve for x. Then once you've solved that inequality for x, then it's easy to find a delta, because as soon as you've located the interval AB, you just choose delta to be the smaller of the distances from x naught to either end of the interval. Now we're going to begin with a problem where epsilon is given and the function is given and we have to find the delta. Suppose f of x equal 1 over x, L is 1/4, and x naught equals 4, and epsilon is equal to 0.05. What we want to do is first find an open interval about x naught on which the inequality absolute f of x minus L less than epsilon holds. So if that's our first step, we want to solve that. And then once we've solved that inequality, we want to then find a delta greater than 0 so that 0 less than absolute x minus x naught less than delta actually always implies that f of x minus L, an absolute value, is less than epsilon. And we want to do that for this very particular setup. This function, f of x equal 1 over x, we want the x naught equal to 4 and the L equal to 1/4, and the epsilon is 0.05. Okay, so that's our problem. So f of x is 1 over x, L is 1/4, x naught is 4, epsilon is 0.05. Now that's 5/100, which is a 20th. And so the initial inequality that we have to solve, absolute f of x, is absolute 1 over x minus a 4th in absolute value less than 1/20th. So that's the same as negative a 20th less than 1 over x minus a 4th less than 1/20th. So add 1/4 throughout, we get 1/4 minus a 20th less than 1 over x less than 1/4 plus a 20th. Now 1/4 is 5/20, so 5/20 minus 1/20 is 4/20. So we have 4/20 less than 1 over x less than 5/20 plus 1/20 is 6/20. Well, 4/20 is clearly 1/5, and 6/20, we can cancel 2's, is 3/10. So what's happened now, our inequality is simplified to 1/5 less than 1 over x less than 3/10. Now all our numbers here we can assume to be positive, so consequently I can turn everything upside down if I reverse the inequality. So this inequality is equivalent to 5 greater than x greater than 10/3. Let's reverse the inequalities now and put it in the order we're used to. 10/3 less than x less than 5. Okay, well, what is 10/3? 10/3 is 3 1/3 less than x less than 5. Where's the center we want to look at? X naught is equal to 4. So see, here's the solution of our inequality. 3 1/3 less than x less than 5. The center of our interval we want to look at is at 4. And so what would be the center, what would be a delta that'll work, that 4 minus delta to 4 plus delta will stay in this interval? Well, what you do is you look at the distance from 4 to 3 1/3. That's 2/3, and the distance from 4 to 5 is 1. And so delta has to be the minimum of those two distances. And so the minimum would be 2/3. So consequently, if I take delta equal 2/3, let's write that down, delta equal 2/3, then we'll have solved the problem. In other words, in this situation, take delta equal 2/3. In that case, if 0 is less than x minus x naught, where x naught is 4, is less than 2/3, that implies that f of x minus L is less than epsilon, where f of x is 1 over x and L is 1/4. All right, now let's look at another problem with epsilons and deltas. Here, I have the function f of x equal x squared, L equals 4, x naught equals -2, and we're taking epsilon equal to 0.5, which of course is 1/2. And so we want to solve the inequality f of x minus L in absolute value less than epsilon. Well, that inequality in this case becomes absolute value of x squared minus 4 in absolute value less than 1/2. And so consequently, that's the same thing as saying -1/2 less than x squared minus 4 less than 1/2. Now add 4 throughout. We get 4 minus 1/2 less than x squared less than 4 plus 1/2. 4 minus 1/2 is 3 1/2, or 3.5. Less than x squared less than 4 plus 1/2, or 4 1/2. I'll write that as 4.5. So here we've just about finished. Notice taking square roots will preserve the order. That is, if I take the square root of each of these terms, then square root 3.5 is less than square root of x squared is less than square root of 4.5. Now, what is x naught? X naught is -2. So consequently, our x naught squared is 4, and the square root of x naught squared is 2. So that is in this range. On the other hand, one thing that we need to keep in mind here is that when I deal with this inequality, it could be that it's the negative square roots we want to look at. Notice the negative of square root 3.5 squared would also be 3.5, and we're looking at x equal to -2, x naught equal -2. So let's look at the situation for taking the negative square roots. That would be negative square root 4.5 less than negative square root x squared less than negative square root 3.5. Okay, Now the negative of the square root of x squared for x naught equal -2 will give us -2. And so this is an interval which contains our x naught equal to -2. And so that's the solution we want to look at. In effect, negative square root 4.5 less than x less than negative square root 3.5. Well, here what we need to do is a computation, and if you do that, you'll find negative square root 3.5. Well, that's about negative 1.87. It's actually a little more negative than that. And square root 4.5 is about 2.12, so this is about a negative 2.12. So the x's that we want to consider are roughly between negative 1.87 and negative 2.12. And so if we want to be sure that our delta is going to be good enough, if we were to take delta equal to, say, 0.1, our center now is -2. Concentrate on that -2 for a second. If I subtract 0.1 from -2, I'll only go back to -2.1, which is not this far to the left. And if I add 0.1, I'll go up to -1.9, which is not as far to the right as -1.87. So in this case, we can see that delta equal 0.1 will actually work for us. That is, in the case where I take delta equal to 0.1, if I require 0 less than x minus x naught, an absolute value be less than that delta, then our f of x minus L, an absolute value, will be less than epsilon. Now let's look at a problem where we actually prove a limit. Here we want to prove the limit as x approaches 1 of f of x equal 1 if f of x equal x squared for x not equal to 1 and f of x equals 2 when x equals 1. Now notice what's happening here. Our graph of the function is just a parabola almost. There's a parabola. Notice the parabola goes through the point 1, 1. That's the curve y equal x squared. But I've drawn a little circle there to indicate that that point isn't on our graph, because for our function, when x equals 1, f of x equals 2. Okay, now remember what we said is that if you draw a vertical line over this x equals the x limit value here of 1, draw this vertical line and just cover up, we now no longer know what specifically happened at x equal 1 as far as the function is concerned, because it doesn't matter. Remember, in the definition of limit, it's 0 less than x minus x naught, which in this case is 1, being less than delta implies absolute f of x minus the limiting value, which is also 1 here, less than epsilon. In other words, this is what we need to show. And what is it that we need to show? We need to show that for every positive epsilon, such a delta can be found. In other words, that delta will be depending on epsilon, and we want to find its explicit dependence on that epsilon. So that's our problem. And notice that because 0 is less than the absolute value of x minus 1 less than delta, that means that x is not equal to 1, and so this f of x right here is x squared, no matter that f of x at x equal 1 is 2. And so consequently, when I go to solve this inequality, here I'll be replacing the f of x by x squared, even though f at 1 is 2. So let's begin by looking at our inequality involving epsilon. Our inequality now is simply absolute value of x squared minus 1 less than epsilon. And what we can notice right off is that x squared minus 1 factors as x minus 1 times x plus 1. And so consequently, we can write absolute value of x squared minus 1 less than epsilon is the same as the inequality absolute value x minus 1 times absolute value x plus 1 less than epsilon, because of course the absolute value of a product is just the product of the absolute values. Now you can see we could solve our inequality for what we like right away. We could write absolute value of x minus 1 is less than epsilon divided by the absolute value of x plus 1. The problem is we're not allowed to have our delta depend on the x itself. It can only depend on the x naught, which in this case is the number 1. So consequently, we have to figure out, well, how small could this get? What is it that makes epsilon over absolute x plus 1 get small? It would be the denominator getting big. So now the question is, how can we control absolute value of x plus 1? That's the question. Well, one thing we can remember is that when we're taking the limit as x approaches 1, we're making x get near 1. So why not write off, just require that the absolute value of x minus 1 be less than 1. That means whatever delta we finally choose, we'll just make sure that it's less than or equal to 1. Now, what can we say about absolute value of x when x can be at distance at most 1 from the number 1? Well, notice if x can be at most distance 1 from the number 1, the biggest x could be is 2, and so consequently the biggest x plus 1 could be is 3. And so that guarantees that absolute x plus 1 is less than 3. So what we can say then is that epsilon divided by 3 is less than epsilon divided by absolute x plus 1. And so here's the way we reason. If we require that absolute value of x minus 1 be simply less than epsilon over 3, then that's going to guarantee that it's less than epsilon over absolute value x plus 1, provided we've also required that absolute value x minus 1 be less than 1. And so that tells us what to do. We take delta to be equal to the minimum of the numbers 1 and epsilon over 3. So no matter what epsilon I'm given that's positive, if epsilon over 3 is bigger than 1, just choose delta to be 1. If epsilon over 3 is less than 1, choose delta to be epsilon over 3. In that case, if 0 is less than absolute x minus 1 is less than our delta, then this inequality holds, and so consequently this inequality holds, and therefore our original inequality holds. And so consequently we found a way to get the delta for every epsilon. Now let's work another problem where we prove a limit. Prove that the limit as x approaches negative 3 of x squared minus 9 over x plus 3 equals negative 6. Now remember, you're using the epsilon delta definition of the limit. I want you to pause the video, try this on your own, and then see how I do it. Okay, so we must show that for every epsilon, for every positive epsilon, there is a delta greater than 0 And of course it's going to have to depend on epsilon, so let me tag it with an epsilon to remind myself of that. So that 0 less than absolute value x minus the quantity -3, absolute value less than the delta sub epsilon, implies, in this case, absolute value of our function x squared minus 9 over x plus 3 minus -6 less than epsilon. Now remember, this provision that the difference in absolute value of x and the limit point here, -3, be positive guarantees that the x in this expression cannot be -3. And notice our denominator here would be 0 if x is -3. So that's a very useful fact. In other words, just having this difference in absolute value less than delta in our argument is not everything. This provision that it be positive is extremely important to keep in mind, because that means we can factor the numerator and cancel. So now let's carry that out and solve that inequality. Okay, so our inequality is x squared minus 9 divided by x plus 3 minus -6 in absolute value less than epsilon. So let's start simplifying. Let's factor the numerator here. So that's x minus 3 times the quantity x plus 3 all over x plus 3. And minus a -6 is the same as plus 6. Now we can cancel the x plus 3's, and we have simply x minus 3 plus 6 in absolute value less than epsilon. That's the same as saying x plus 3 in absolute value less than epsilon. But notice x plus 3 is the same as absolute value of x minus -3 is less than epsilon. So notice this inequality is equivalent to this, is the same as this, is the same as this, is the same as this, provided x is not equal to -3. Well, notice this is very simple now. Here's our limiting point, the x naught, and so we're finding absolute value of x minus x naught less than epsilon for x not equal to -3 is exactly the same as the inequality x squared minus 9 over x plus 3 minus -6, all in absolute value less than epsilon. So in this case, it's very easy. The delta sub epsilon is simply taken equal to the epsilon. Let's look at another problem where we prove a limit involving a trig function. Here we want to prove the limit as x approaches 0 of x times the quantity sine 1 over x equals 0. So remember, what we have to do is for every positive epsilon, we need to find a delta which will depend on epsilon, positive, so that 0 less than absolute x minus, in this case, 0 less than the delta sub epsilon implies absolute value of x sine 1 over x minus 0 in absolute value is less than epsilon. Notice how important this provision that this absolute value of the difference be positive is in this case, because sine 1 over x is undefined at x equals 0. So we certainly can't have x being equal to 0. Now, absolute value of x minus 0 is just absolute value of x, and likewise absolute value of this quantity minus 0 is absolute x times sine 1 over x. And so consequently, this inequality is the same as, just looking at those two terms, absolute x times absolute sine 1 over x less than epsilon. Now here, let's ask ourselves, how big can sine 1 over x ever be? What do you know about the sine function? Remember, the sine function is always between -1 and 1, and so consequently this quantity right here is always less than or equal to 1. And that means this whole thing on the left is less than or equal to absolute x. I'm going to just write that, less than or equal to absolute x. Notice it's absolute x less than delta that we're looking for to imply that this quantity is less than epsilon. So if this whole thing is always less than absolute x, then all I have to do is take the delta equal to the epsilon. If I take the delta equal to the epsilon, this inequality would be the same as this, which would imply this, because that's even bigger than this. So we just take delta sub epsilon equal to epsilon. Okay, we've discussed the precise definition of a limit, and we've worked some problems with the precise definition finding deltas given epsilons, and we've proved some limits using the epsilon delta definition of a limit. Remember, when you have to do this given a specific epsilon, solve the inequality absolute f of x minus L less than epsilon first, and then find the delta.